Welcome to this session on target elimination, where we deal with why we need target elimination, what is target elimination, and how to do target elimination. The first part of the series will cover why do we need target elimination. The need for a target elimination is rather not obvious. The need for a target elimination stems from the fact that we need to make better decisions to understand what really works in real world conditions, whether in case of clinical practice where we try to make decisions about using treatment A or treatment B, or in case of public health situations, we try to implement community-wide intervention or a screening program. These are inherently causal questions where we want to know about the comparative effectiveness and safety of interventions under study. The goal of causal inference is to estimate causal effect of an action on an outcome, be it hard sciences like biology, chemistry, or physics, where they primarily depend on experimentation inside a lab under controlled situations. Soft sciences like epidemiology, economics, public health, or sociology often turn to observation. In essential, not all questions are causal. The causal questions that we face on a day-to-day basis in clinical situations, for example, does liver transplant surgery increase the life expectancy of individuals suffering from cirrhosis? On the contrary, non-causal questions like how many people in India have early onset dementia, which is largely a prevalence study, the estimate of which will be a proportion measured as a prevalence of early onset dementia in a country. Does childhood obesity correlate with mental health problems in adolescent years, where the primary aim is to measure correlation between a risk factor and an outcome? This question is essentially non-causal. So, how to answer causal questions? Primarily, we depended on designing randomized control trials. RCT is considered as a gold standard for evidence generation in medical decision making for a long time now. Let's take this ideal situation where we try to evaluate a perfect vaccine using a well-designed RCT, where we start by recruiting a number of participants, randomize them in a 1:1 ratio between vaccine or a placebo or even another candidate vaccine, and follow them over a set period of time, let's say 1 year, and record the stated outcomes. We analyze the data of this particular RCT based on intention to treat principle, where the data is analyzed according to the treatment they were assigned to. On the contrary, let us imagine another drug, a less perfect situation, where the recruited number of participants are randomized 1:1, taking a drug for 3 months compared to a placebo, and then followed up for the same period. Eventually, this particular data is analyzed according to intention to treat principle. The participants are analyzed according to the treatment they were assigned to. But what about the other ends? There comes the causal contrast of analyzing the same data, considering per protocol effects, where we take into the adherence of the drug by the participants. This essentially gives us a causal contrast for us to estimate the causal inference. Causal inference relies on 4 main assumptions: exchangeability, positivity, consistency, and non-interference. When it comes to exchangeability, it relies on the assumption it requires that individuals who are exposed and unexposed have the same potential outcomes on an average. This essentially means there is no unmeasured confounding or no selection bias. We have not conditioned or restricted on a variable that is a common effect of exposure and outcome. What is positivity? It simply means that positivity, if you want to compare 2 types of exposure, then you have to have people in your data who are able to and sometimes will receive any or all of the relevant exposure values. This essentially indicates that there is a non-zero positive probability of receiving every level of treatment, allowing some individuals to be assigned to each of the treatment groups. Then what is consistency? It essentially requires that the exposure is sufficiently well defined so that each individual has one potential outcome for each level of exposure. The clear specifications of treatment levels, like well-defined interventions and well-defined causal questions, are essential for this condition. And when it comes to non-interference, the non-interference assumption requires that an individual's potential outcome and hence the causal effect does not depend on the exposure status of anyone else in the same study. This assumption can be violated by spillover effects of some exposure, for example, vaccination, in a study which aims to measure the effectiveness of a particular vaccine, where an individual's outcomes are affected by the exposure status of those who are around. Thus, RCTs are generally known to be great for causal inference. When we estimate intention to treat effects in RCTs, randomization becomes our exposure. Randomization ensures no confounding at baseline for treatment assignment. Also ensures positivity for treatment assignment, and it's a well-defined intervention. Intention to treat analysis often gives unbiased estimates of intention to treat effects. In a hypothetical vaccine trial compared to an hypothetical drug trial, where we can't move quite so quickly, the treatment and loss to follow up after randomization. Post-randomization events are not guaranteed to be unconfounded. So, the causal inference is possible on a hypothetical vaccine trial when compared to the drug trial. Ideally, we would like to construct or conduct a randomized trial to inform our decisions, but it is not always the case. Most of the settings are too expensive and just not feasible, can be unethical, and the results won't be timely enough for us to make meaningful decisions when it is actually required. Instead, we can tend to rely on observational studies to give us some valid answers, where data which are derived from classical epidemiological studies like cohorts or case control studies can be interpreted, analyzed to give us valid answers. And there is a new data which is available to us, new arena of data which is available to us from what we call as the found data. The larger databases which are derived from electronic medical records, insurance and administrative claims databases, and national registries or disease-specific registries. We want to conceptualize observational studies designed in found data as a conditionally randomized experiments. Remember, this is not our preferred choice. Of course, observational studies always have the risk of introducing bias into our inferences. Biases like confounding, selection bias, and measurement errors are very much possible. We need to look at this problem and we try to solve this using causal inference techniques. Thank you.